In this lab, we will predict the future motion of a falling object using Newton's second law. In this case, the future motion of my new pair of socks. To do this, I collected motion data from a video that displays the socks falling using Tracker, then created computational models in Python using Newton's second law, and finally compared the predictions of the computer models with the motion data from the video. Using Tracker, I recorded myself dropping a sock, as you've already seen. Unfortunately, the best frame rate I could get was 15 frames per second, so the amount of data points that I could collect before the socks touched the ground was less than what I would have hoped for. However, the amount will still suffice. I placed the origin of the y-axis fairly close where I let the socks go. For the computer to accurately understand what the distance between each frame was, I set a collaboration stick that extended from the top of my shoulder to the middle of my knee, which was estimated to be about 0.9 meters. As you can see from this graph, the total duration of the experiment was 0.4 seconds, and the initial position where we start our analysis is at 0.007 meters in the negative y direction. Since it's so close to the origin, which is 0, it's hard to visually see the difference on the graph. The object is also initially at rest since it's being held in my hand. Using Python, I constructed computational models with Newton's second law that should accurately predict the sock's motion after being released from my hand. Since the velocity is changing over time, we have to assume that the net force must not equal 0 due to Newton's second law. If that's so, then there must be at least one outside force acting on the object while it's in midair. Even though the object is not being touched, the earth force, or weight force, is what's pulling the object towards the earth. Upon opening Python, I input the following system properties and initial conditions for the experiment. The ball's mass, which is approximately 0.013 kilograms, the ball's position, which I've said before is 0.007 meters in the negative y direction, and the ball's initial velocity, which is 0 because it is at rest. Of course, the time we started the experiment is also at 0 seconds. For another initialization, we have the time step, or delta t, which I've set to 0.04 seconds to make it easier to compare with the smaller amount of data that I collected in the video analysis. We then have the proportionality constant g set to 9.8, being the magnitude in newtons of the gravitational field near the Earth's surface. We will use this to help calculate our sock's weight force. Ending our initialization, we have the rj hat, which is used to specify the direction of the weight force, which is along the y-axis. Now is where we put Newton's law and predict the object's motion. I set the duration to be that of 0.39 seconds. This is different from my experiment, which was 0.4 seconds. The time step I had chosen before made it so that it went a bit too far over 0.4 seconds when I ran the program. When switching to 0.39, it ended 0.399 repeating, which is pretty much exactly where I wanted to end. Predicting new velocity is the same as Lab 1's, where the final velocity is equal to the initial velocity plus the product of the net force and change in time over the mass. This also goes for predicting the new position, which is its initial position plus the product of the ball's velocity and change in time. The equation with delta t simply has it go to the next time interval by adding the new time step. For the net force, I determined that it was equal to the weight of the force of the object, which is the negative of the ball's mass multiplied by gravity, and the direction vector j hat as we've already defined previously. We then set that equal to the net force so that it is used in Newton's second law equations. After running the program, you can see the motion of the object going downward as well as a graph that looks similar to the one of the video analysis. After further inspection, we can see the beginning of our graphs match up nicely, but the rate of change in the sock's velocity begins to decrease. This implies that there is another force at work here that points in the opposite direction of the weight force, and increases as the sock falls further down. This is the air resistance that the socks experience while falling, which is also known as a drag force. Drag force is equal to some constant b multiplied by the velocity of an object, which explains why it increases the longer the socks are falling. To get the constant, we must plug in numbers so that the final position of the computational model will be equal to the final position of the experimental. Here I found 0.031 Newton seconds per meter to be the best number. To make more accurate prediction from the computer model, I went back and added the drag force to the weight force, which produces a different net force to be used in Newton's second law. To show the direction and magnitude of both forces, I created two arrows that would represent them. To get the magnitude, I multiply both arrows by an arrow scale that can be altered but be altered to make the direction and magnitude of the forces easier to see. After trial and error, I found that an arrow scale of 8 meters was optimal. After running the program, you can see the bigger arrow represents the weight force, while the smaller one, pointed in the opposite direction, represents a drag force. We now have a new graph, and after comparing it with the previous one, we see that all the points from our experimental data match up with the line produced. Therefore, we have found the right neck force this time and successfully predicted the future motion of a falling object.